Okay. So I will talk about ABC, which some of you may not know about because it's hidden within USS. Anytime you run USS, it will do synthesis and mapping, and that is done by ABC. And my name is Mishchenko. I have been developing open source code for about 25 years. And 20 of those years, I was with UC Berkeley, where I collaborated with some of the greatest people who worked in this area for a number of years. And all this time, I was the main developer and main debugger and main person to contact about ABC. So give you an overview of what the system is doing. And I hope I will have some time for questions. Yeah. So I have a lot of slides, so please excuse me if I'm flip through them too quickly. But this presentation is available, and you can either download it from my website, or I share it with Olaf, or just email me and get it. There is some recipes will be here, which may be useful for projects which you're doing. So first of all, let's find out where we are. So in this long spaghetti list of steps which involve computer design, there is a small step in the middle called bit-level logic synthesis and mapping. So this is where ABC belongs. It does have some word-level features, and it can occasionally communicate with physical design. But this is where we are. Even though it's such a small step in a very long flow, it's believed to be one of the most challenging, and it requires most of intellectual rigor, perhaps. So some people call logic synthesis a crown jewel of EDA. As a crown, it should be on top, but it somehow ended up in the middle. So interestingly, I work on it for 20 years. There is so many things to do and so many things to improve and scale up. So it looks like this work will continue. And fortunately, all of this is in public domain. And feedback from you will inspire me and guide me in my future steps. So I'm talking about verification also, but we understand that verification may be needed to compare different snapshots of the design, let's say between system level, between RTL level and gate level, or between different steps in gate level. So all these methods which you develop kind of equally apply to synthesis and verification. And in historical perspective, I guess some early designers started working with truth tables around 1950s. Then there was a notion of sum of products. And at IBM in particular, there was a number of SAP minimizers developed. First Minis, then Espresso. Then my supervisor, Professor Brayton, finished his career at IBM and became professor at Berkeley. He brought a lot of this stuff with him to our group, and he has been advising PhD students for 30 or 40 years, and tools such as MIS, SYS, Viz, and MVSys have been developed under him between 1980s and 2000s. I joined Berkeley in around 2002, and we started kind of improving and deepening those kind of ideas which were already existing. And one of the things, we moved from SAP to BDDs in the 1990s, but then BDDs turned out to be very non-scalable. So we moved to AIGs and CNF. And so now we solve most of the problems without BDD package, without sum of product minimizers such as Espresso. We pretty much work with this data structure called AIG. If needed, we convert it to CNF. If needed, we use various types of simulation, which looks like to approximately represent a function, we can just use a bunch of simulation vectors. This is, we believe, like the best data structure we have so far. It scales very well, and it allows us to solve many problems for very large designs. And of course, with multi-core implementations, we can now partition designs and do it in parallel. So just the sky is the limit. But basically, just to say that ABC stands on the shoulders of the giants. It has a long history. And right now, it's based on those best data structures we could find. So I'll talk about ABC on a basic level as a Boolean calculator and visualizer. I'll show some commands and scripts which could be used if you play with ABC by hand. And unfortunately, advanced level will have to wait for some other occasion, but there are some packages which I'll list. And then as part of my self-criticism, I will tell you what I believe was the best part or the hit of ABC and where I missed. And again, as an open source developer, I'm very happy to hear criticism and suggestions. And if you don't like what I do, you can also do it by yourself and teach me how to do it. So we will kind of wrap up with this self-critical part, and then I'll show some research directions. So let's look at the Boolean calculator. So we can use ABC to read and generate small functions or small Boolean networks. And we can either come up with a network from scratch or take it from an available design. And then we can compute various functional properties such as symmetries, decomposability, unateness, whatever we may need to look up when you read textbook on logic synthesis or you do a little course project, ABC can be used as a kind of handy calculator for this. So it can do things like minimize SOP, reorder BDDs, extract kernels or divisors from an expression. It can visualize the result in BDD. You can output an SOP and also look what the products are. And visualization is done using this dot file generated with path to GSView. It's very easy to set up. Basically, as soon as you download ABC, compile it, you just install GS, or it's called the package in Linux is called GV, and then it will start working right away. So standard command scripts would be, if you move from like this hobbyist use to trying to do something in terms of technology-independent synthesis, then some people start with representations in terms of PLA, and they want to compile them into networks and see what the quality will be. Then there is, of course, technology mapping for standard cells and lookup tables if you already have a design available and you want to do something with it. More advanced use cases involve sequential synthesis, where you have a sequential network and you try to, let's say, minimize the number of flops or do some retiming to reduce the length of combinational paths. And of course, all of this is supported by verification. Because ABC has both synthesis and verification, any transformation you have applied can immediately be verified by, within ABC by typing additional command. So this is just a very quick idea of what AIG rewriting is doing. This is our main workhorse when it comes to transforming or minimizing logic networks. So we pre-compute a certain library of small AIG subgraphs. And AIG stands for And-Inverter Graph. It's a Boolean network composed of 2 input AND gates and inverters. And it's believed to be like one of the most generic, most useful data structure for small functions as well as for millions of gates. So we pre-compute those subgraphs on the left-hand side, and then we see if there is a way to replace one small piece by another small piece, like here, this is supposed to be an arrow. But we take 3 nodes and replace them by 2 nodes, or we take another situation where there is some external nodes already available, and we replace, in this case, this node in such a way that one of them is saved. So this is all done automatically. You don't have to follow it, but I'm just giving you an idea to see what ABC is doing inside. This is a very simple peephole optimization. Try to reduce the number of nodes and maintain the number of levels. Alternatively, we can try to minimize the number of levels, which may increase the number of nodes. Then we can hit it again with node minimization, and we iterate it. Since these scripts are very fast, we can iterate them 10 times. And in many cases, we can achieve much better results than if we have one complicated, very complex computation, which is applied once. 10 iterations of easy scripts like this would actually perform better than one strong logic synthesis implementation. Now, when it comes to technology-independent synthesis, these are some scripts. And if you're not familiar with ABC, you would need to learn basically some of these commands and how they apply. But if you use USys will call all the scripts for you. And in many cases, they're doing a good job in terms of selecting what needs to be done. So you don't have to understand this. It really depends where your interests are. So many designers or people who play with the logic synthesis tools will begin by specifying a PLA file. Here I just show a very simple PLA file to represent a half adder. Half adder has 2 inputs, 2 outputs, and so you can just list all input combinations and see what the output would be. So if you present your circuit in this format, you can read it into ABC, and you can follow suggestions on this slide to synthesize it, and you can again do various things with it, minimize for error, minimize for delay, and eventually can map it into a library or map it into lookup tables. And you can always verify it against the original specification. So that's one of the typical use cases. Technology mapping actually looks at this AIG, which has been optimized already, and then it tries to cover it with lookup tables. And here we see, call it subject graph, just 2 input nodes, and on the right-hand side we see lookup tables. Again, we have a number of mappers and a number of features in those mappers. Some of them map only into plain lookup tables. Some of them can map into so-called programmable cells. Of course, there is standard cell mappers there too, with many caveats. Standard cell mapping is not as easy as LUT mapping, but still, with those caveats, ABC can be used and has been used by major companies to do technology mapping. And there are, of course, references. I'll list one of them here. So these are various commands. You can read either simplified gate representation in genlib format, or you can use actually Synopsys Liberty format, and it will extract delay and area parameters from that format, and even wire delay models and other things as needed. And all those mappers will be able to apply mapping. And sizing has not been particularly popular in ABC, but there are commands which allow you to do static timing analysis using these two-dimensional table models coming from Liberty file, and then do some kind of buffering, fan-out optimization, and then do this upsize, downsize. This is an attempt to do sizing. So sizing in ABC is very fast, and it seems to work well, but the buffering is not very good, so the overall flow is still somewhat shaky. But with more push, with more requests, I guess we will upgrade this. And if ABC is useful within OpenRoad or other projects, I hope we can nail this down and make it better. And structural choices is one of the ways to improve the quality of results. Let's see. Similarly, mapping for lookup tables also has a few commands which you may try. So this is one of the kind of distinguishing features of ABC against other tools. Normally, a tool would go through a sequence of snapshots, D1, D2, D3, and arrive at a final snapshot. In ABC, we actually accumulate multiple snapshots. For example, D1 can be an original design, D2 can be optimized for delay, and D3 can be optimized for area. We can take all three of those, combine them into so-called history AG, and then do technology mapping over all snapshots, including those which have good area and good delay. This tends to improve some of the parameters, and this, again, technology has been in ABC for about 10 or 15 years, and it has shown quite a good feedback from the users. So I will skip some ideas on sequential synthesis. It's rather advanced stuff. And in verification, basically, we can take two copies of the design, whether it's combinational or sequential. We build this miter. Miter becomes another circuit. It's another AIG. And then we have to prove that this miter is equivalent to constant 0. So if it is equivalent to constant 0, those designs always produce the same outputs. If we find one particular input sequence which would lead to a non-zero at the output, it means we found a bug. And so ABC has a bunch of engines for both model checking and equivalence checking, which are quite good at finding bugs and also occasionally good at proving pretty hard equivalence checking problems. So again, those have been used. So ABC has been a building block of this system called SuperPro, which was a winner of hardware model checking competition for many years since we started participating until about 2018, where we stopped participating. But all those engines are available, and they can be called either as a single engine verification job, or you can put in a flow, and a flow can possibly simplify, retime, partition, or abstract, and then use induction to prove the final miter or whatever is left of the final miter. OK, so I still have a few minutes. So in terms of advanced features, I don't have much to cover. I'll just mention an AIG package. So basically, AIG is this very handy data structure which we use. And here I show two. The same function can be represented by multiple AIGs. The top one has 6 nodes, 4 levels. The bottom one has 7 nodes, 3 levels. And they're functional equivalent, but we don't know which one to use. So ABC would kind of derive multiple structural representations and put them together into this AIG with structural choices. And then when technology mapper comes along and tries to map, they will use either delay optimal or area optimal, depending on whether this piece of logic happened to be on a critical path or off a critical path. So this is all done automatically, but we kind of appreciate the generality of this. It works for any circuit structures, small or big, and it's all automatic. And moreover, it doesn't even seem to be so computationally expensive. It seems to be quite scalable for even, can be applied for million node AIGs, which corresponds perhaps to some of the largest FPGAs we have right now, and maybe corresponds to one typical ASIC design block. OK, so I will skip some of the particular features of AIG package, which is designed after BD package. A lot of work has been put in to perfect those data structures, to make sure we save every byte of memory and every microsecond of execution time. So there is this notion of minimalistic AIG package, which uses only 8 bytes per node. And it's almost like your own construction set. You can construct a package which is best for your application without having any memory overhead. So if you begin to program in ABC, you may appreciate some of these minimalistic features. So now a quick overview of what ABC achieved and what it did not achieve. So it is based on cutting-edge research ideas. It offers low cost and often competitive implementation of fundamental algorithms. It tends to be fast and low memory. It's reliable if you use it in a known way. Some of the new users always find new ways to use ABC, and then they come up with very unusual bugs, which I've never seen. But if you just pretty much do whatever I recommend in this presentation, you'll pretty much never see crashes. But if you want to see crashes, you can see them very soon by just going off on your little trail. And it's actively developed, and it's supported. So if you have any questions or ideas how to contribute or how to improve it, please email me. And when it comes to ABC limitations, it doesn't have its own Verilog parser, but fortunately we can use USys as a parser. So as I mentioned, ABC is integrated into USys, but independently I integrated USys into ABC. So when I'm running ABC, I can actually use USys to read in any design, and I continue working on it in ABC. So kind of we benefit, both projects benefit from each other a lot. And it doesn't, I think one of the limitations of ABC, it doesn't always support this industrial stuff. And so that means complex flops, multiple clocks, memories, design constraints, all of that. So there is some elaborate workarounds are sometimes needed. And again, this is my shortcoming. I should have seen the future of ABC and developed all this stuff early on. But I was very much in a kind of academic researcher, just happy writing papers and programming easy stuff. And when ABC started being used by industry and by open source community, it's a little bit too late to add that stuff. But fortunately, USys circumvented many of this. And I have a bunch of other tricks to circumvent the remaining ones. So it seems to be OK so far. And documentation is poor. I'm sorry. I'm working on it. And there is a lot of redundant code, which shouldn't be a problem if you don't look into the code. And so lessons learned. So having a variety of formats is useful, but of course having Verilog is very important. Need the well-documented APIs for integrating into external tools, which is to some extent addressed. And if not clear, please contact me. Then in terms of optimization flow, it's good to have an AGS unifying data structure. It would be nice to support more industrial stuff, as I mentioned here. Data structures, I always say, please develop a clean, minimalistic data structure for whatever you're doing. It reduces memory footprint. And the more memory footprint is reduced, the more runtime is reduced. So it's true about AIGs, logic networks, hierarchical netlists, whatever we're using there. And whenever possible, use 32-bit integers as opposed to pointers. That also helps compress memory footprint. So I strive for maintainability, minimize dependency between packages, strive for reproducibility, thread safety, and try to spend my time working on a good set of APIs from which I can then build more complex applications. So nothing much to say in terms of future research. So we are still working on many aspects of ABC. In particular, we try to integrate simulation and set in a new way. We do some kind of memory abstraction using, let's say, word-level optimizations and so on. And again, there is a connection between ABC, logic synthesis, and machine learning, which is also an interesting way to explore this kind of joint space. So these are some of the supporters which supported ABC since 2005. They have been very, very helpful. In particular, government agencies, NSF, NSA, SRC has helped a lot. Otherwise, I would not be able to maintain my soft money position at Berkeley for 20 years. And so they basically allow us to continue, build, and publicize all this work. And these are contributors to ABC. Again, a list of people who wrote their code and either personally or in a roundabout way helped me integrate it. And if there is any other contributions which you think would belong well in ABC, please contact me. I'll be happy to integrate your code. And there is various resources here. There is, of course, GitHub webpage. There is a tutorial written by someone. There is Windows binary, which hasn't been updated for a year or so. And overall, if you have patience and time to figure it out, ABC can be very useful. If not, you can just use it within USys, and it should be fine. If you have any questions, please don't hesitate to contact me. And consider contributing anything you like. For example, you wrote code for your paper, or you have a course project, and you believe it's generally useful, it belongs within Logic Synthesis Tool Suite, please contact me, and we can try to integrate it. Thank you. I think this was my talk.
Thanks very much, Alan. As usual, I have a first question. You mentioned it implements a lot of like kind of cutting edge research ideas.
Yes.
How far away do you think what you're implementing is from the cutting edge of kind of proprietary cadence synopsis tools?
I think occasionally we're ahead of them.
Yeah, right.
This is because I'm talking to some of the industrial people, and I learned that they still use whatever 20, 15-year ago ideas, but we productized in ABC and proven the concept of many of the new ideas, which are kind of making their way into industry. But of course, it's not general. There are some exceptional industrial ideas and industrial teams which are ahead of ABC in some ways. But overall, when it comes to synthesis, I think we're maybe on average we're ahead of them, or maybe we're on par. They may have something more better than us, and we have something better than them. So fortunately, ABC is available for everyone, including those industrial companies who want to benchmark their tools against ABC. They can always do this. And occasionally they tell me that they learned something useful, and I hope they improve their own tools as well.
So first of all, I'm happy that we got you to come here. We tried many times,
Yeah.
but it has never worked out before. But I mean, ABC is really a cornerstone project of this.
Okay.
So when you say a node, is that kind of equivalent to an AND gate? So how large design, do you know what a large design is that someone have used ABC with?
Okay, so it of course depends what usage is, because people use ABC for so many things. I would think synthesizing a design block, like sequential or combinational design block with 1 million gates, which would roughly correspond to 1+ million AIG nodes, is doable. Runtime may not be good, but we also know that industrial tools also have long runtime. So for some specific tasks, let's say sweeping or proving equivalence or doing some other easy computations, ABC can scale up to 100 million AIG nodes. This is also okay. Most of the workstations have lots of memory, so ABC would just allocate a large chunk of memory and put all these nodes there, even if there is. I think the current limit we have in our package is 500 million. But again, that limit could be removed. And in fact, in one of the student projects I'm working now, they're trying to make a special flow which would scale up to maybe 4 billion nodes. This is what we see now. But there was not that much need for such high scalability, at least up to now. I know there will be more need in the future. This is why we're kind of forward-looking. But overall, 100,000 nodes is a very typical size for us. 1 million nodes is more or less okay. More than that is questionable. It depends what you're doing.
So yeah, this is a great project, but so if you have like a PDK with some mux cells, maybe like an adder cell or so, like more larger things, can the AIG algorithm still be used to optimize when you're dealing with like cells that are optimized on a transistor level?
Yes, so there is many optimization use cases. In one of them, you will take your logic, whatever it is, flatten into an AIG, optimize AIG very hard, and then remap it into your library. Another optimization would be to keep your mapping as much as we can, and then locally optimize it, doing some kind of post-mapping resynthesis. So ABC has both ways of working with designs, and it actually depends on your preference, depends on your runtime budget, depends on how much improvement you expect, and how important it is to preserve your current mapping. Yeah.
Great work, high impact. But I have a question. How will you compare with the mock turtle? Because it's more or less the alternative I can see that we can use. So what is, besides the code and quality of results, how do you compare?
I'm very closely collaborating with everyone involved in mock turtle team, so I know what they're doing. Indeed, in some ways, they have outperformed ABC. Like they have a very nice technology mapper which works with multi-output cells, which ABC doesn't have. Recently, they have some new delay optimization package, which again, ABC doesn't have. Then in the past, I collaborated with someone in mock turtle teams. They developed some simulation guided resubstitution. Again, very nice feature, and I didn't have time to backport it into ABC. So indeed, some specific transforms are on par and better in mock turtle. And we're actually talking about integrating these tools together, because if mock turtle is kind of becomes part of ABC, I can maintain it and make it available to all of you guys for foreseeable future. Meanwhile, if for any reason mock turtle team stops developing, some of those great implementations may be lost. So I would think most of the critical stuff are present in ABC. If you're not chasing the last 1% improvement, ABC would be okay. But mock turtle has many good ideas and many good implementations which could be added to ABC as well. That's my take.
Okay, let's thank Alan again. Cheers.
Thank you.